Alright, here we go. CIS-125, day 4, programming. Here's what we did. We looked at review, we looked at a little bit of VI and Linux. We got to do more on that. We really got started a good job on control structures and top-down design. So these are the main things we covered today. First thing I did, we started out talking about reviewing. The students actually wrote up some work. They talked about source code. I said, what happens, can they explain what happens with a compiler or interpreter to end up with executable code. That process, and in that process define both of those. So the students wrote that out on some scratch paper and then turned those in for me to look at. When we talk about having a processor, memory, and storage, they should be able to, given that, explain the process that takes place when a program is executing. Processor, the arithmetic logic unit, and registers. They should know those things. In the session before, we looked up the flowchart symbols. So what we did here, the students looked those up again before we started in on the control structures. Peer, we're going to use peer review, peer check, either both online and in class. Okay, so when you do your work, we're going to show you a checklist to do that. So then I took ASCII and I wrote a number. That's actually my office phone number. So we're doing a little review of that binary number system, which I said is important. And I said that 6, could they come up with the bit pattern that represents that 6? And the students did. And then what we did, we wrote it down up here. And then I wrote the powers of 2 above here, 2 to the 0, 2 to the 1, 2 to the 2nd, 3rd, 4th, 5th, 6th, 7th. 2 to the anything to 0 power is 1. That's a math thing. 2 to the 1st is 2. 2 to the 2nd is 4. 2 to the 3rd is 8. 16, 32, 64, 128. 2 to the 7th is 128. So we figured this out. We got one group of 32. We got one group of 16. I'm getting that from these up here. Then we had one group of 4 and one group of 2. Add those together and we get 54. So the decimal 54 equates to, using ASCII, a 6. And that's not the number 6, that is the text or the representation of 6. We'll keep reviewing these topics as we... Alright, so our control structures for programming. First one is sequence. Everything functions in a sequence, one after another. Now these particular boxes are process boxes that we use to represent that. You notice we have arrows going in the box and out of the box, in the box and out of the box, and they just touch and they have the arrows. Those are flow arrows, and those rectangular boxes are function boxes. So then we did a little example. All flowcharts and pseudocode or any design for programming have a start and a stop. One start, one stop. And in this case you can see the flow moves from one box to another. That's why we refer to as sequence. Now this box, we have an action word and then we have actually a variable there. I define the variable over here in the legend. Right there. Radius means radius of a circle. So this is an action word input. This box is an input-output box. This box is a process box, and then we have another input-output box. All three of them have an action word. They all say to do something, and then we actually do the work. Here we calculate on the right, and we store it to the left. We have this variable here called area. In the legend, we say that area is the area of a circle. We create some test data to test this. So in our flow, we start, we input the radius, we take the radius squared times pi, store that in area, and then we print area is area. Over here, we did a walkthrough. We took and went step by step. Step, radius was nothing, area was nothing, no output. Input, we put in this, nothing, nothing. Then we did the calculation, step 3. So 1, 2, 3. This, send that to the processor. The processor puts that in a register and then does the arithmetic, puts that in a register and then sends it back to memory in this location. And then 4, the print right here, we didn't actually print this, but the radius still has that value in there. We printed this text right here, and then we printed what was in the area. Right there, you can't see it all right there, but it's right there. So we only tested one piece of data, but we could try the rest of our test data if we want to. So sequence. Then we briefly covered, conditional. I tend to call it conditional. Some people refer to as selection or decision. We have this ability. We made a diamond here. 1 arrow in, 2 arrows out, but it always must come back together. So into the structure, 1 arrow, coming out of the structure, 1 arrow. Okay, a decision box, it makes a logical decision, for example, something greater than something. If it's true, we do this processing, could be a sequence or whatever. If it's false, we do this. Or, in some cases, if it's false, we don't do anything. Okay? So it's conditional. Or you can call it a selection or decision. We either do the processing this way. So if hours are greater than 40 true, we figure overtime over here using that. If not, we figure pay without overtime. Then we bring it back together and then do whatever work we're doing here. Next one's an iteration. Iteration, we have a connector, and then we decide if we're going to keep looping or not. We make a decision. This is a leading decision called a do while. And so we do while the decision is true. We go down, do the work, and then we come back up to the connector and back in. There are no processes between there and there. That might seem simple today, but you'll be surprised later on you'll want to put some processes in there. So we continue the loop until this statement becomes false, and then we continue on in the program. Leading decision, it's an iteration, it's a loop, it's a leading decision. We also have a trailing decision, and we'll talk a little more later on about for loops. 2 more pages. While we were working, we created the all-important checklist that we're going to use to do peer review. And somebody can use it to do their own self-review of, in this case, our flowcharts. Are the symbols correct? More or less, is a parallelogram is a process, a diamond. Can you identify the symbols? You can look at them, see what they are. Flow lines touch the symbols, they don't go in or out. Process symbol, we have 1 arrow in, 1 arrow out. Everything has an action word, every line. All program designs have to have a start and a stop, and only one of each. The flow should be down and to the right. Do not cross over any flow lines. Must have a legend. Test code walkthrough, need to test the data. Self-test, peer test. Formulas always. We've got the variable on this side, the formula on this side. We calculate over here and store it there. Documentation, there's all kinds of stuff in the syllabus about documentation, and then we're going to learn about doing a peer review. So we have a checklist that's not complete. We're going to add more to it here in the future. Alright, so to finish up, control structures, they're like a blueprint. Okay, they're like a blueprint. You couldn't build the World Trade Center without a blueprint. The more difficult the problem to solve is, and we're going to use software and computing technology to solve the problem, the more important it is to have a really clear blueprint showing the process to the solution, so many people can look at it and understand where we're going. Okay, so control structures, we use flowcharts and pseudocode. Pseudocode's false code. You write like code, so this is more of a text view, and this is more of a diagram view. And we're going to work with both. That's it.